Are we going? I think we are going. I think we might be going. Oh, need the microphone closer. Hello, hello. All right. Stream manager, here we are. Learning Rust. I need to change these titles. My chats. Let's pop that out. Yeah, but can we? My chats. Pop out chats here. Cool. Now let's do the YouTube one. Here it is. Cool. And chats. There they are. And here they are both. Okay. I think we might be good. Let's just change the titles. Have they titles? Zig Advent of Code. Zig Advent of Code. Plus. There we go. And yeah. Okay. Welcome everyone. So yeah, one viewer, which means me. But let's act as if there's a lot of people here. So I want to continue with my Zig stuff, my Zig Advent of Code. I've had a couple of videos out the other days doing Zig and doing Zig Advent of Code, but I kind of want to take a slightly slower approach. That's why I decided to stream, because I'm pretty sure day 17 requires some pathfinding. Minimizing heat loss in this path, yeah, so it requires some sort of pathfinding, and I actually don't know how to do this sort of pathfinding, because I'll just show you the example. So these are the heat losses that you take from going to each one. So you want, the problem is to get from top left to bottom right, and the numbers very much mean distance. So that would be great if you could just go from top left to top right, but there is a condition that says, because it is very difficult to keep a top-heavy crucible going in a straight line for very long, it can move at most 3 blocks in a single direction before it has to turn 90 degrees left or right. Okay, so there's even more of a restriction, left or right. Up, left, right. I mean, you're not going to go backwards where you just came from, I guess. Yeah. So, what do I think about this? I think that... Oh, we can only also go one. I need more theory about this. I actually have not really got any clue as to how to start, so... Reddit, Advent of Code. I kind of want to just jump straight into here and have a look at some of the people's help for day 17. We could have a look at solutions. I reckon they will have it. Yeah. 2023. Archive of solution maker threads, solution maker threads. 2023, and I want day 17. Yes, the clumsy crucible. Breadth first search approach with a priority queue. It's interesting. I'm actually not sure. Let's have a look at this guy. I'm glad I stepped back and came to this problem later without time pressure because it was more fun just going iteratively. Because it was more fun just going iteratively step by step. The key for me was building a graph from the grid where every square has two association vertices, one to indicate you've arrived from a horizontal direction, another to indicate you've arrived from a vertical direction. Then you have a direct connection to each of the three squares. Or 6 for part 2. Oh, okay. That you can reach. So horizontal vertices only connect to vertical ones, vice versa. And then it was only a matter of implementing the extras. Yeah. Okay. So we got some extras. And you know, it might be good to just write a pathing algorithm in, you know, like this. I'm actually gonna just turn off the screen for a sec. Sorry guys, sorry. I just want to share the stream with a couple of friends. Okay. Now, how do I share a stream? Oh my god, I suck at this. Oh. Channel. Yeah, here I am. Just sharing it around. All right. Let's actually close Discord before someone says something wacky. Okay. So from just kind of a quick understanding of the solution. What is this? Hello Mano, how are you? This is a programming stream. We're doing programming, and we're going to learn about pathfinding algorithms. If you are interested, I'm fine. Good. I'm glad. What's Code doing? Code is going to find. Okay, I'll show you. So you have this here, which is kind of like a maze, and you need to get from the top left to the bottom right. And all the numbers are kind of distances to the next part. So you need 2, and then you need 4, and then you need 1 if you go like in a straight line. But obviously you want to find the shortest way. So maybe you'll go in a straight line for a bit, then you go down, then down, maybe right, whatever. You find the shortest path, and there's algorithms for that. Dijkstra's pathfinding algorithm. And this is kind of what we're going to be implementing. Something you always learn at school when you do programming. It's fairly kind of like standard. Oh, what is this appearance? It's cool. Dark. That's better. So we're going to be implementing this, which gives you, fairly good stuff. And then we actually have, it's funny enough, I actually implemented a priority queue in a previous project, so I'm probably going to bring that in. I implemented it on my Huffman encoding project, which was interesting. What's the chat? What would you need something like that for? Pathfinding. What would you need pathfinding for? Millions of things. I mean, first of all, the obvious one is literal pathfinding and maps, right? Google Maps, not only of distance, but of time. Pathfinding in circuit boards is kind of interesting because electrons, speed of light can sometimes be slow, relatively speaking, obviously, with electrons. Anywhere where you need to get from point A to point B in the most efficient way possible. There's a lot of there's other type of algorithms like max flow problems that can simulate like trains, for example, so it can optimize traffic. So like you already have like quite a few pretty big ones. Transport is a huge reason why pathfinding algorithms are so useful, and obviously in games, video games, you're going to need pathfinding algorithms for. So yeah, and Dijkstra is a type of algorithm that is guaranteed to give you the shortest path after a while. There's other algorithms that actually games will actually implement because it's faster. The A-star search algorithm, which is a variation of Dijkstra's. But it's a variation of Dijkstra's, but has a heuristic to make it quicker. So on average, this runs faster than Dijkstra's, but is not guaranteed to give you the best path, which is interesting. And I swear I'm boring everyone already. So maybe I'll just stop talking. Yeah, I bet everyone, well, me and you, I bet we're bored as hell already. Okay, but thinking about this problem, the part that makes it a little bit more difficult is that it's not just a straightforward path-finding algorithm because there's other limitations. You need to move at most 3 blocks. So that means you can't go more than 3 in one direction. You have to change direction. So as I've kind of been spoiled by this very good explanation by this guy on Reddit, I knew it was a pathfinding algorithm. I wasn't sure how people take what approach people were taking. But I think what we have to do is not build a direct graph from this. We can't just go this to this to this to this. We have to build a graph that goes from here to here, from here to here, and from here, I feel like there too. Yeah, because you can move 3 places. So you actually, per thing, you need quite a few edges. So there's 2 parts to this problem. There's the actual pathfinding, after you have like all the edges and nodes and stuff like that. And the breaking down the input into those edges first. When's the first John P. Costa game going to be released? Oh, I have a feeling I have. It was one of my very, very first... Actually, it was my first project that I released. It's here. Can I... Does it work? Yeah, johncosta27.github/snake. There you go, I'll put it on the chat. I made it so long ago. It's one of my favorite projects still. It just works. It's like super simple snake game. I'm proud of how it came along. It was it was great. I was learning about canvases and stuff. And how old was I? I was 17, maybe very, very young. When I did it, and I remember having a ton of fun with it. All in all, it probably took like a Saturday, and I just never touched it since. It was just a very short project, and it just worked. It just worked. Obviously, I'm sure the code isn't great anymore, but yeah, I'll just die. There you go. Just restarts. One thing I remember I was really, really happy about was the zoom. I can't actually zoom out very well. Yeah, it's interesting. If I zoom in a bunch, you see the screen actually gets smaller. So the number of tiles is adapted to your screen size. So if I zoom out a lot, you see it's going to have, a lot of them. And then you have the proper margins on the top and left and the bottom. I was very, very happy with this. Yeah. What is this input lag? It's 75 milliseconds. Because it works on ticks. So 1000 divided by 75. The game is 13 ticks. 13.3 recurring ticks. So it's kind of slow. But if you made it any faster, it becomes very difficult. And if you check for inputs before, then you'd need animations. Because I don't want to get for the game to be fast. So it's kind of it was a weird problem. Because you want the game to be very quick and very responsive, but you don't want the snake to go too quick, so you don't want that many ticks. Or you don't want like moving from one box to the other, which is what I consider a tick. So yeah. Anyways, it was a fun game. You can actually, I think the code is just very, very plain. You can go over here and you can have a look at the code. Snake.js. Yeah, literally no obfuscation and nothing, just code. Just 300 lines. Very simple. Very simple code. with some very global states. Yeah, this brings back so many memories. A little bit of mobile there. We have the page load, the window request animation, the redrawing. That's not very efficient, is it? Yeah, a lot of logic. Yeah, this was cool. I remember this was really fun. Restart equals 1 or 2. What was restart? Oh, it's okay. Fair enough. Cool. And then is mobile and stuff. It's cool. And yeah, that's what I was talking about with the screen size. Okay. Wasn't there a game you worked on at school where you made your own sprites and sounds? I did, but I kept it at school. That school project. It wasn't very much a school project. It was actually this one wasn't actually a school project. The snake, that was all me. But the sprite one was at school, at college. But that stayed there. I wish I had the ability to learn that. You do. Everyone does. It's just where if you want to sit at the computer. All right. Thank you for joining. It was fun talking. See you soon. Have a good one. All right. Let's continue. Let's continue with pathfinding. Okay, I have an idea. Now, what to do? Advent of Code. Here. So, let's do some dextras. Should we run it here? Yeah, I guess. Let's go, actually let's do source and let's do graph/graph.zig. And we can do our unit test here and stuff. At import standard lib. And let's just test hello world. I can't even remember how to do tests. Oh, it's a try, isn't it? Const expect equals standard dot. Where's my LSP? No LSP? Give me LSP, bro. There we go. Dot testing dot expect. Expect true equals true, and then we have to try. Zig Advent of Code Zig test dot /source /graph Zig. There it goes building, and it works. And if I make it fail, then I'll make it fail. There we go. Cool. Let's start off with some graph. With some nodes. So const node equals graph node, just node, equals a struct that's gonna have basically nothing. It's gonna have in nodes and out nodes. Should we just care about out nodes? Yeah, we should, because this is a directed graph. A DAG. DAG. So we can have out nodes, which is an array. Do I do arrays like this? Or is this, or am I writing Go? Yes, this. Yeah, cool. Array of edges. So const edge struct in node, which you're going to be a pointer to a node, and the out node is a pointer to a node as well. Oh, it's array of pointers. Pointers of edges or just edges? Think just edges, something like this. Okay. Can represent simple graph. standard.heap.test allocator, base allocator, let's call it page allocator. I haven't actually experimented too much with allocators because I haven't really found the need to optimize down to that level, but I might in the future. I think I do have a GPA somewhere here. Yeah, general purpose allocator for some stuff. But I don't even need an allocator, I think. Just do stack memory. Constant n1 equals node dot out nodes equals an empty array. Constant 1 equals n dot out node. I feel like that's not how you do it. Zig empty. Okay. How to create empty array slices. Is it just undefined actually? That's it, yeah, undefined. Node, out nodes, undefined. Const E1, which is edge 1, let's just go from dot in node, which is a pointer to n1, and then the out node is a pointer to n2. And then we actually go n1 dot out nodes equals 2 const edge n1 out nodes which, oh god, Zig.guide, nope, oh here, arrays, so yeah, that's it, an array of some size of an edge that contains E1. Or we can probably go n1.out edges out nodes equals to this, and we expect n1.out nodes dot length to be equals 1, and try expect n1.out nodes at 0 dot to be equal to E1. Expected type graph node found constant. Can I not do const here? Guess we can put constants everywhere just because we don't really need to. Can I assign to constant? True. Maybe I need pointers here then. Pointers, edge, A1. How's this? No. An array of pointers to an edge. Let me take the pointer for that. Okay. Cannot assign to constant. Oh, right. Okay. Wait, what's it on about? Yeah, pointer of edges, and it takes the array literal requires address of operator to go as type. Yeah. What do you want about? Oh, like this here. I'm confused. Array literal requires address of operator to go as slice type. Okay. The address of? No. Oh, I can't remember what this is. I need to remind myself. So, more Zig learning, that's why we're here. Useless compiler error. Oh, is that actually how you meant to do it? To just discard? So if I do const edge array, I do n1.outNodes equals edge array 0 dot dot, then that doesn't do it. Boys, I'm having a silly moment, I think. Having a silly moment. Trying to create some arrays. Doesn't like it. So then I would assume that I could take the address of the whole thing and that would work. Oh, is it because it's not constant? If I do const there. Okay. At address. That's it. Array. Edges. I wonder if you have the same array. No, you fell, so it's a copy. It's copied over. Well, okay, well, we have something that does work. We have something that does work. Okay. Now we need to create some dijkstras. We need to do some dijkstras. The algorithm uses a min priority queue data structure selecting the shortest path known so far before more advanced priority queue structures were discovered. Is it talking about a heap? Once a heap. And our priority queue is done with a heap, so it doesn't actually matter. Okay. To remind myself, mark all nodes as unvisited. Create a set of all the unvisited nodes called the unvisited set. Assign to every node a distance from start value. For the starting node it is 0, and for a lot of nodes it is infinity. Since initially no path is known to these nodes during execution of the algorithm, distance of a node will be discovered. From the unvisited set, select the current node. Is that pseudocode? Yeah. So for each vertex v in graph.vertices, the distance from v is infinite to the previous undefined. Add v to q. Q distance to sort q while q is not empty. Okay, so this is the stuff that we know. Yeah, vertices here. Okay. U vertex in q with minimum distance. Remove u from q. Okay. Sounds good, I think. Okay. So I mean, for this to do some work, we're going on the vertices of v in graph dot vertices. Okay, let's think about this a bit more. All of them. Previous at v is undefined. Okay, we're just initializing stuff. Add v to q. Then the distance from the source is 0. That's the initial node. And then while there is basically for every single vertex, we're going to say whilst it isn't empty, u is vertex in q with minimum distance u. Remove u from q. Okay, well, this is always infinite, right? This is always infinite, I thought. I'm actually kind of confused, to be honest. Okay, well, we remove u from q. For each neighbor of v... Oh, wait. That's it. You start from the source where the distance is 0. So you're gonna pick the source every time, and then for each neighbor v of u there. So for every vertex of u still in the queue. Okay, so an extra check there. Yes, and whether the priority queue would come into this is getting the minimums here, right? Because you want to push things and pull things, and you want them all to be sorted in a priority queue efficiently. So that involves then the heap underneath. That's what I did for Huffman. For the Huffman encoding. Yeah, Huffman's. So I did the heap and the... Well, I just did heap. Yeah, and this worked quite well. Yeah, a couple of tests here. I just realized that the people on YouTube... Hi, it's Max. Hello, Max. The Orca 6. Ah, could have guessed. Maybe I missed you, actually. Fair enough. Let's continue. Dijkstra's, doing some more Dijkstra's. Lost where I was for a sec. So after this, for each neighbor v of u still in q, alt dist u plus graph plus. Okay, what does this mean? Variable alt is the distance to u, so this is like kind of the accumulated distance, plus the graph dot edges from u to v. Oh, yeah, so one edge from u to v. If the alternative distance is smaller than the distance to v, then we change that and we continue. Nice. Okay. Dijkstra's test set. Looking for a... I want very small kind of graph to test this on. Yep, very cool. Now can I get some distances, please? No distances for me. Shame, I guess. Let's create them. So let's also give each node a label, which is an array of U8. Dot label equals n1 and 2. And let's start off super simple. Test. Can find shortest path between A and B. And this test will involve A and B and C and D. And let's say oh wait, hold on. Just formatting. Oh, I can't exactly do it. Let's call that 4. Let's call that 3. Let's call this 1. Let's call this 3 as well. Let's call it 4. Actually, let's say 5. So shortest path is from the top. So let's start with 4 nodes. Out nodes equals undefined.label URA B, C, D. Then let's go const AB equals edge with the in node as a pointer to A, the out node is a pointer to B. Nothing else? No, nothing else in the chat. And then we have B to D, B, and then A to C, and then C, D. C, actually A, C, C, D. A dot out nodes equals pointer to an array of edge, which is AB and then AC. And then 2 more of these. We'll see there. B to D, and then D has no out node, C does, however, and this is going to be CD. Okay, so this is the setup, and we actually need to perform the algorithm. So func fn. God, I completely forgot how to do functions. Yeah, function like I always mess this up. So Dijk, D-I-J-K, Dijkstra's. Okay, so we should probably wrap this up in the future. Actually, yeah, let's do this now. Const graph equals a struct that's going to contain the nodes. Yeah, it's just going to contain all the nodes. Const node. That takes in a graph, and you are the graph. Expected return statement. Did you? That's it, yeah. Const graph equals graph edges, which is an array of node A, B, C, D. And let's just have Dijkstra pull out shortest path. So it's going to be usize shortest path equals Dijkstra's with the graph, and then expect shortest path to be equal to, was it 5? Yeah, it was 5. And this should return 1, and then this should not work. Unused function parameter, that is true. Can I cast you into void? Yes, I can. Error in the union is ignored. Let's do a try. Cool. Do I need a new line there? Kind of. Let's get rid of it. Okay. So the pseudocode has me keep. Can I do this whole thing in stack? So I don't need basically anything at all. Hey man, how are you doing? Wizard from the 9th layer of hell. It's a great name, man. I'm doing okay. Thank you for joining the stream. Hope you have a good time. I'll monitor the chat maybe every 5 minutes or so. Let me know if you have any questions, any thoughts, ideas. Yeah, cool. Let's continue. So I'm actually going to just paste the pseudocode for Dijkstra's here, so I can see it kind of constantly. We need to keep a couple of maps. So distance, previous. Previous is like the current work map. And this maps a vertex, so an edge. Wherever you see vertex, I mean edge. To a number. So if I remember correctly, there is a stack allocator, stand.heap.stack allocator. Zig stack allocator. Oh, but it's buff. Yeah, it's. Okay, let's take in an allocator then. We'll let the caller decide what they want to do. Here we can just have const page allocator equals stand.keep.page allocator. We can have test allocator equals standard.testing.test. No, heap.test allocator with the initial allocator, which is a page allocator. And we can pass this over to Dijkstra's. Anything else from the YouTube comments? No questions. I have zero clue on what you're doing. Just chilling for the vibes. Hope you don't mind, Kek. Of course I don't mind. This is cool. What is the Advent of Code overall problem? Yes, so it's day 17 from last year, 2023. And it's kind of a pathfinding algorithm. So I'll start from the top. We have some lava. We have a crucible that we're trying to get across from the top left to the bottom right. So from this top left all the way to this bottom right. It's top heavy and pushed by hand. Unfortunately, the crucible has become very, very difficult to steer at high speeds. So it can be hard to go in a straight line for very long. So you can start to see like the limitations of this. We can't just do regular Dijkstra's, we need to put something on top of it, but we still need regular pathfinding. To get Desert Island, the machine parts it needs as soon as possible. You need to find the path where you minimize the distance. They call it heat loss here, but it's just distance. But you can only go 3 in a straight line, so the max you can go is 3. So you can't just take this and put it in a graph directly. You have to go ahead and transform this into a special graph so that you have this edge connected to this edge, and then this edge oh god, my tab previews. This edge connect this edge, and you kind of have to do multiple edges per node. Oh my god, what is going on there? So you can't just do this connected to the right, top, left, and bottom. That's really, really annoying. You have to do the ones twice away from it, 3 times away from it, so that you have the actual shortest paths and stuff. So it's a more complex pathfinding, but at the bottom of it, it's still kind of pathfinding questions. Cool. Let's continue. So yeah, day 17. If you're curious to have more of a look, that wasn't the greatest explanation, but okay. Right. So here we're gonna have a couple of things, I guess. So we're gonna have for an array list. No, this is a hash map. A hash map between pointers. Pointer values. Yeah, I think that makes sense. Also, I'd have to have right. You need to have some sort of identifier for the edges. Do I? No, I don't. Okay, let's just do var distance map, which is standard.hash auto hash map, which takes in a key, which is an edge. I guess we can take in a pointer of an edge, like we're comparing pointers more than anything, and a U size, and we're gonna have a work map, which is gonna do the same. From here, we're going to the distance map. Oh, and we need the source. No, oh wait, no, vertices do not mean edges. Vertices mean actual nodes. So yeah, this is distance to node, not distance to edge, so that makes no sense. Oh, that's kind of annoying, because what do I pass in here? The label? That doesn't seem right. I must point, has to be a pointer. So let's try dot put source and 0. And then while q, add v to q. Oh, that's my priority queue. Stand dot priority queue. Oh god, just thinking about this. It's actually not straightforward to have a priority queue here. Is it? Because it needs to minimize distance to you. And yeah, that's not straightforward at all. Maybe I just keep an array for now, an array list, and then we change it to priority queue once we understand this a little bit better. Yeah, let's do that. Let's get the algorithm working first. Then, once we understand it a bit better, figure it out and actually do it with the proper runtimes, proper big O n times and stuff. Okay, and then a work map and a work queue. Well, not really a work queue. But you are going to have the work queue. Remove you from queue. Yeah, that's where this would be super useful to be a thing. But what do I minimize on? I minimize on something. I see, that's an interesting one. Yeah, it is. You minimize on distance to you. So the node might need some sort of caching. So the distance to the source. Node dot distance. Maybe we do keep something on a node, on the nodes themselves. Yeah, maybe we do. Let's do. It's kind of ugly. We could do like an underscore. Underscore to make sure it's private, but no. I don't like this approach, but we'll go with it. Work distance, so use size. And now we can actually have a real priority queue. And the priority queue is going to be a node. What else do you take? Priority queue takes a node. Comp time context. Don't quite understand that one. Comp time context. What are you? Void, I guess. Priority queue for storing generic data, initialize with init provide compare function where the second argument should get popped for its third argument. If the arguments are equal, then blah blah blah. Go to context here already. I don't really understand what this context thing is about. Where do you use it? Just context, self.context. Just don't understand. I'm gonna just do void then. Assume you're good. Then the compare function. How did this happen? I need an actual like compare function. Node compare. Oh, is that where the context comes from? Okay. Constant view size then. That's going to be node compare. And we're going to initialize this with our allocator. And you are going to be a node. And the node a dot work distance. I think we want you all to be pointers actually. So, because we want to mutate the data underneath, we want to make sure we don't have any copies. And I did want to do some Zig footgun things very similar to this, related to copying structs and using certain data structures they provide. That I faced the other day. Use of undeclared const order equals standard dot math dot order. Okay. Now we have our work queue. Okay. And then add v to queue. Add v to queue. Oh, then actually I should have this first up here. Just after the distance map. The work map, the work queue for each vertex we in the graph. Yeah, okay. For graph.nodes, we're going to do work. We're going to do a few things. We're going to do distance map. Distance map dot put the node, pointer to its graph.nodes, and again no copying, so an array of pointer of nodes. So node is very much a pointer, and I'm going to put in very, very large number because we want to kind of represent infinity there. Previous, so this is our work map, isn't it? Try work map dot puts a node as undefined. Where do we use previous? I can't remember. I don't. We'll figure it out in a sec. Actually, and I'd add v to queue. Work queue dot push on queue. Locator init add insert new elements. Yeah, we're gonna insert node. And you can error out. So let's go through this. While work queue, I need a parenthesis here. Queue dot size, no. Init remove update capacity iterator remove on null and shows all capacity from items dot length. Each time it goes around items dot length. Is it items dot length? So maybe we just do peak whilst it exists. I'm kind of interested by its implementation of items here then. Add. So ensure unused capacity, add unchecked. Items.length. So you are actually mutating length manually. And remove on null, self.remove index 0. You are changing the length. So it is safe to do work queue dot items dot length. It's bigger than 0. Okay. Rest of pseudocode requires me to have const closest node equals work underscore queue dot. I could do this in the same statement actually with the loop. I could make a part of the loop. But anyways, removes and returns the highest priority element from the queue. Oh, actually, I just remember that this needs to be the other way around. Return your other, yeah, this needs to be a B here and A here because we want, like, we don't want a max queue, we want a min queue. Very similar thing. So let's remove it. Closest node. For closest node dot out nodes edge. We're gonna have our const alternative path equals 2 the distance map dot get the key that is closest node dot question mark, yeah, because we want to guarantee that's there, plus graph dot edges between U and V. Do we know that? So V, wait, for each neighbor V of U, oh, right, so we have the edge that connects the two. Wait. Closest node, this gives you a node. Out nodes. Okay, I see where I'm getting confused. This is out edges. Yeah. Edge. So we have an edge. Edges even. And then this is kind of going through each neighbor. Const neighbor equals edge dot out node. Okay, so for each one of these we're going to do const alternative path equals neighbor, oh, not that, neighbor dot graph edge to new V. So actually we want the edge, we want the distance, because we are connected the closest edge to this current one, so edge dot, funnily enough, did not add distance. Distance, oh god, whatever that is, dot, no, stop, there you go, 5 or something, and 4 dot distance B to D1 dot distance A to C3 dot distance equal to 5. Out nodes dot, not out node, actually edge just distance, that's it, and it wants me to add it to Okay. Yeah, so we go through we go through all its neighbors, see if we can find a shorter alternative path to that new vertex, because then we set it to v, and then yeah, that's it. Okay, here we go, distance map get node is view, so it's actually the closest node dot question mark plus this. Okay. The distance map, not that. This map is between you sides, so that will work. And then if the alternate path is smaller than the, oh yeah, because we set it to 9 and 9, distance map dot get of the neighboring node dot question mark. Then we go try distance map dot put the key, which is the neighbor, and the alternate path. And we do also do work underscore map. Oh, this is the paths, right? I get it now. From, yeah, okay, I understand. So this is actually node to node. Try work map dot put. The neighbor is the key, and the value as the closest node. That all passes type check. I think I remember missing out this work map thing up here. V is undefined. Null. I think we can probably have a null pointer. Can we have null pointers in Zig? Probably can. What happens here? No field out nodes. Instruct. So do we still have out nodes anywhere? Out edges. Great. Missing struct field work underscore distance. So wait, I don't need that anymore, do I? No. I got other things. Expected type for found something. Found what, bro? Oh, I need pointers to all these. Okay. Oh, and I need to type that correctly. I mean, expected type something something found something. Okay, can I do an array of pointers? Or is it? Yeah. Okay, so they wanted an array of constant pointers, and they found a constant pointer to pointers. Yeah, that sucks. Actually, I'm not sure how to solve this. What if I do const star I don't even kind of want to know what this is, so const nodes equals, see what this is. So you are pointer to pointer. What do you say, compiler? Okay, do this to disregard the other thing. Expected type, an array of constant pointers, and we found a constant pointer to an array of non-constant pointers. How's this? Far? Okay, that was something. Yeah, it's confusing, but we got it. The extras wants a source too, and the source is A. Expected memory allocator found. Not a memory allocator. Oh, I need to do a try. Wait, what? What are you? Test allocator. This one should not try alignments. Okay, well, maybe just go away then. What else? Variable of type must be constant compile time. Distance called map. Oh yeah. Dot init with the allocator. Dot init with the allocator. Expected U size found something. Distance map dot put source. Found what? Expected U size found error out of memory. Oh, you have to try those. Does init throw? No, doesn't look like it. So wait, init doesn't give me an error. Do I not need to try to put into hash map? It's kind of news to me actually. Error union is ignored. So try. But then expected type U size found error out of memory. Oh. Right. Yeah, this has to return an error. Okay. Okay, expected error union. Let's go map. Okay, I don't need to do a try there. Expected type function math order found. Expected type found. Oh yeah, U size there. Expected two arguments found one. Did you? What's the second argument? Context. What is this context stuff? I still not completely. Oh, the nodes. You can start with a literal empty array, I think. Yeah, okay, I get what it is now. Let's just do const empty node array, which is an array of pointer of nodes. And the context is going to be an array of constant of pointer of nodes, I think. Wait, is it? No. 0 dot. So when I put something in the queue, it does so by comparing the distances. And we would do the queue, we add node. Oh, work distance still needed then. Oh, okay. Okay. Because I need that to be part of the queue. Damn, doing so much work. What the fuck is this? Bro is on his villain arc to hack Google. Supernova explosion fire. Well, you know, what can I say? It's some coding. We're doing some coding today. We're doing some Advent of Code. It's a bit late, but we are. I mean, YouTube seems to be doing Advent of Code well. 2 watching, fair enough. Yeah, let's continue. Okay, we're actually going to need allocate usize and then of the length of oh, sorry. Empty array, not so empty. Context here. Okay. And the work distances will just be 0 bunch of the time. I mean, are they? I'd love an example with structs, you know? There's no example here with structs, which is annoying. I mean, this is the actual standard library, which is great, but where is my with context comparator? Okay. Okay, let's continue anyways. I mean, I kind of understand, I just don't. There's no the comparison function, which is going to compare It's going to compare indices, so like left and right. Let's go back. Context list then. Okay, so these are actual indices, not values per se. Well, this is the array of nodes, and then this would be the positions. Okay, so I'm kind of thinking about this the wrong way around. This should be a usize. This should be usize, and then this should be an array of pointers of nodes. And then dot work this, and that's it, I think. That's it, this here. And the other way, wrong way around, because we want min, not max q. And what do we need to change here? So the word q takes in the com time, which is node, and the context type is an array of nodes, node comparator, and the context Context is for now going to be empty because it starts empty. So var empty node array pointer node. That's it. We can do something like this. Missing structural work distance in line 81. 0, 0. Dot work underscore distance equal to 0. 0. Cool. Okay. Expected type function that takes an array of graph nodes to graph node. Am I? Shouldn't it be usize? Why should you take in an array of... I'm so confused by this structure. So it wants... Take in node A and B, and how do I compare that node A and B are smaller than, and where does this context come in? What if I just ignore that? You know, I feel like it won't go well, but nope. This unused function parameter, context not needed. Getting pretty tempted to just use the queue I made myself, the priority queue I made myself a while ago, but seems to be getting happier. So expected type graph and constant. I mean, yeah, you are gonna have constants here. Distance map, and then the work map is also gonna have constant nodes that won't be changed. Oh, can I not do this? Because the work map will always just be... Oh, I don't need to initialize it if I'm not actually doing anything with it. And work queue. And then this pointer, constant pointers, no mutating. Work map dot put. Oh yeah, this is also between constant. This is a nice feature of Zig. Very nice feature to prevent memory errors. We have some compiling. Okay. We have some compiling, guys. So let's actually go between the work map. Iterator item the iterator print any of the item work map iter, the iterator creates an iterator, work map iterator dot, isn't it? I swear it's just, you just use them. Iterators. Yep. Oh, while try next. Okay. Item. Okay. Item dot key pointer, item dot value pointer. Did you not work? Zig test print to stand out during tests. How to print standard out when running tests in Zig. Uses the progress utility to emit output to generate a line of content without a new line. Be careful with print, causing tests to run in parallel, so this can cause crashes. Have a look at standard log. Log standard.log. So instead of print, log.info. I mean, I would love to have some output here, just to make sure that this is fine. If I return 5, this will work. Yeah, but it doesn't log. Log.info, hello. Let's try this. No, nothing. Dot print bruh. Okay, so print is working, but it is that simply put work map dot length count 0. Okay. You know what I'd love? I'd love a debugger right now. I'd love some debugging. W from Dexter Brown. Hello, Dexter Brown. Cheap views at ysntech.com. I'm okay, but yeah, thank you for that. Can I ban people? How do I ban people? Well, if I could ban you, then I would, but don't know really. Don't know how to, so. Okay. Let's work through it. Closest node dot. There is a label to every node for this exact purpose. Let's try it. A, then B, then D, then C. So it goes from A to B, then it should go to C. Has this context really come back to hurt me? Has it? You know, let's take a look at CD Huffman's, because I have a heap here that is literally just a priority queue and doesn't take in any of this faffing around. So let's just try it very quickly. to use it over here in our project. .nem, there we go. And at least it's code I wrote, and I kind of understand as well. Okay. Let's try this. Instead of priority queue, we can do the heap, which takes in a type, and then the compare function. And to initialize it, you just need an allocator and to do a try. Now, does it have an add? It has a there's a remove insert, that's what I called it. Work map, work queue. Okay. Like this. Work queue insert. It's funny, insert doesn't take in just, oh, because it doesn't actually, it's not very safe. It's not very safe. Oh, it just goes to 64. Yeah, okay. Funny number. Yeah, it never really expects more than 64 in at the time. This will very much have to change. Max items equals just make 10,000. There you go. That's why insert doesn't actually make an error. Doesn't have field called items. You are correct. Work queue dot array dot length. Oh, did I really call it array? Should actually be called items. Oh no, it's not. Point plus equal 1. Yeah, that's what I want. Bad at naming. Very bad at naming. A D. Hold on 1 sec. So it goes A, then D, then D. That can't be right. That cannot be right. Because I'm working on work distance, and that's all 0. Whereas actually, I should be changing work distance here. And I should be going, yeah. Is this where that context part? I'm starting to understand the problems now. Which is really annoying. And the worst part is, yeah, this distance map. I'm gonna have to use work distance, which means I'm gonna have to make a lot of stuff mutable, which means potentially a lot of headaches. But yeah, and I'm mutating this on the node level. It's actually not great. So damn, yeah. Don't you love it when things you do just come back star dot work distance is equal to 9999999. This is closest node dot work distance plus that distance map, the neighbor dot work distance, neighbor dot star dot work distance equal to this. There you go. And now, yeah, tons of errors. Cannot assign to a constant. Can you not be a constant then, please? Just constant point, so it needs to be mutable. I need to be able to mute. Is it that or is the underlying thing? Yeah, this should be something the other way around. Type errors, give me them. Give me some type errors. Let's just give it a U for a sec. Okay. So let's just make you this. Oh, that was it? Oh, that's pretty nice. You don't need this test, it was just kind of to try things out. A still goes to D. I need to do this after, don't I? A, then it goes to D. Closest. Okay. Dot label. Okay. Closest is B and C, and then it goes to D. Closest is B and then C. No. You're doing it all wrong. What am I getting wrong? I don't think I'm getting anything wrong because of the way the algorithm is set up, to be fair. They've all been put in the queue. And then the closest B and C. The alternate path is the closest node dot work distance plus edge dot distance. Edge distance alternate path. Damn, really thought this would be easier. The edge path to B is 4 and C is 3, that's correct. So then smaller than the neighbors of work distance. It's going to be like 999. It's going to change neighbors dot star dot work distance equal to alternate path. And it's going to put the thing. And let's do a print of this state. For all the graph dot nodes, print work distance and dot work distance. Okay. Work distance for this one and dot label. So work distance 0, 999, yeah, that's all good. From B, the edge distance 4, the edge distance 3. Then it goes on to the next loop and prints some state. It knows that the distance between B and C, oh yeah, so every time we change the work distance. We need to like actually change things through. Yeah, we need to like rebalance it. Yeah, we need like, wow. Yeah, this is I'm starting to completely understand why that context thing was needed, because this is not changing any underlying structures at all. The work, like changing the work distance, because as soon as I do, it becomes unbalanced and I need to balance it again. But it's that the neighbor dot distance, it's changed. So now I need to check. Oh yeah, God. Yeah, I get it now, boys. Yeah, I get it. Big kind of L right now. Yeah, so this is just me being stupid. So the work queue is just gonna be, yeah. Okay. Let's be very silly and just do stand.ArrayList and destroy the runtimes of our beautiful algorithm. Work queue.insert.append. We do a try there. So what's the work distance? Find shortest, which is on time. This is going to take in our, this should have pointed to an array, standard.ArrayList of type star_const node, and it's going to return star_const node. Well, shortest equals 9. So 9 for list.items item if shortest is if the item dot work distance is smaller than the shortest index, let's say 0. List that items at shortest index dot work distance is equal to return there. Shortest index. Okay. I think that should be good. And then inside of our thing here, we can just do find shortest, pass in a pointer to our, with our array list work queue. That's not so much queue anymore. Then we find closest node. Give me type errors. No field name pointer. Well, work queue. Find shortest. So, I mean, we want to take this, the underlying pointer, and then remove it. So we want to go for q dot remove the element at index I, just element after I. Yeah. Find shortest index, usize, shortest index, closest node equals work queue, closest node index. Am I going to get a cheeky out of mem cheeky segfault, do we think? If we all do an ordered remove here, because then this is going to point to, yeah, this is definitely like a segfault. I don't know, actually. Let's try it. What do you say? Q.length.items.length bigger than 0. Okay. Oh, I can actually go const closest. Score node is this. Okay. This is all good. So it goes from A to C. C, the closest is D, the edge now is 8, correct? From A to C to D is 8, from B the closest is 5, and then all the way to D is 5. Okay. I think we have working system, boys. I'm going to just leave these print statements where they are, because that was very useful. So the algorithm was working, just data structure's wrong. So I'll make a note here. This is for sure the wrong data structure. Properly look at priority queue. Good. Properly look at priority queue. And the thing now is that we have this work map that we have a bunch of nodes. And if I'm correct, we should solution, let's just make sure, work map. And where do we want to go? Because we can give it the source and the destination. Destination. Pointer to D. Oh yeah, dot get. Dot get. I feel like I keep trying to write JavaScript. Dot work distance. Whoa, that's too little. What did I give it? D. Oh, sorry guys. Work map dot. Which one should we do? Should we do value iterator? Yeah, we should, right? Const value iter equals work map underscore iter work map value iterator. Dot no, this is while it has map v node v dot work distance. That's it. What do you get? Okay. This isn't how I use iterators. Oh wow, I have so many viewers. What's going on? Not on Twitch. I have a bunch on YouTube. I have WSG, yo, hi, hey everyone. Sorry, I haven't been paying much attention to, well, to YouTube chat, just because, oh wow, and it's super dark. Didn't even realize. There we go. That's just so much better. Yeah, I haven't been paying attention to YouTube chat, I guess. Are you coding for a 3D model? No. Although this would be really cool. I'm coding for an Advent of Code problem. 2023 day 17. But more well, I'm actually coding the dexterous pathfinding algorithm in Zig, which is needed for this problem. And actually, funny enough, I've never implemented it. I've always used BFS, breadth first search solutions, but those are kind of wrong because they're brute forced, whereas it's actually a concrete search algorithm for shortest paths. So cool though. Yeah, thank you, man. Hope you enjoy your time. Let's get on with it. So, I was gonna look up iterators actually. This, and I need try. That looks not great. Yeah, I don't. What's going on here? Why can't I just iterate over you? Yep. Oh, is it because it's const? I need a var. That might be it. Yeah. V dot. Oh yeah, I need doubly stars, don't I? Because it's a pointer to a pointer. Because I'm pointing to. That's weird. I don't know. Not even sure how Zig solves that problem. That's a doubly pointer because I'm pointing to the value that is then pointing to the work list. Because I can do this dot this dot. There you go. You see, now that's the concrete value. Pointer of pointers. Solutions 4 is a solution 4. Solution is not actually 4. I feel like you're going on to B. Yeah, I feel like this is incorrect. Yeah, this is incorrect. It looks very correct, but it's not correct. Let's get some print statements again. Right, so when we are at B, here, the closest is D and the edge distance is 5 total. Then when we get back round to D, we mess everything up because you can see work distance here is all correct. We get 0, 4, 3, 5, that's all good. From graph.node, so maybe I should just look there, but it feels like this work map is not being used properly. Because the work map is setting what v.start.label. Let's try that again. Distance from a dot key iterator. If I iterate over keys. Yes, that's it. Oh, okay. I misunderstood. So the key is the node that you want, and then the output is going to be the node through which it is fastest to get to you. Yeah. Okay. So the solution is actually... Oh, actually, in a very funny turn of events. Destination.workDistance. Yeah, because we're mutating a ton of state here. That's so funny. He was there all along. The friends you made along the way. Actually, I can get rid of this because I'm pretty confident in this now. Nice. You working? You are working. Shortest path. A to D. Let's try a couple more things like B to D. B to D and A to C. Shortest path A to D. You know, because the Dijkstra's can get them all. Set the work. Do you set the work distance to 0 each time before? No, we set it to 0. Okay, cool. Yeah, work distance is mutated. So, and then B to D. I mean, it's super simple. Should just be 1, and then A to C should be just A to C should be C3. Let's try that again. No, it's not working. But to be fair, oh, D to D, yeah, that's not right, is it? And then A to C, there we go. Cool. Oh wow, that was a lot. Oh, Dijk. Oh my god, how do I spell his name? D-I-J. Kstra. Okay. Dijkstra. Dijkstra. Working algorithm with array list. Need to make it better and use an actual priority queue. Okay, that was really productive and really fun. I mean, all you need is Wikipedia, some pseudocode, and you really understand the algorithm. I mean, you know, you give me a piece of paper, I can do this algorithm super easily. But, you know, implementing it, especially in a language like Zig, and figuring out all the memory stuff is not super straightforward. All right, let's look at chat. I want to code some time. You should, man. A really good place to start, if you're still here, is if you add on over to adventofcode.com. You know, just this. adventofcode.com. It's a super cool website with really fun projects. If you go over to the events, and actually if you look at last year's 2022, go to day 1, and this one specific, I'll put it in the chat for you. Like, go on YouTube and look up how people do this. Pick something easy, you know, JavaScript, Python, one of those languages, or and yeah, you'll not have much fun, to be honest, because coding is really frustrating. But when you get it right, you'll get, hopefully, an incredible feeling that you will become addicted to, and then you just do that for a living, banging your head against the computer until things work. And then eventually things work. Like, I mean, look at what happened today. I knew about Dijkstra's, but again, I'm still unfamiliar with Zig, even though I've done the entirety of the Advent of Code in it, and another project, Huffman's, in it. I'm still not the most familiar guy with it. But I kept going, you know. You just gotta keep going, guys. After, how long has it been? 2 hours? 2 hours of just some very simple code at the end of the day. 124 lines is just not that much code. And to be fair, I haven't even pushed this to its limits, so it could just fall apart, to be honest. It looks promising, and it looks like it's working well, but, you know, as you do. Right, guys, thank you so much for watching, genuinely, whoever tuned in. I really do appreciate you. This has been really fun, and hopefully I'll keep doing more of it soon. Yeah,